Distinguished guests, distinguished delegate, ladies and gentlemen, my name is Liu Jianbang, a PhD student in the National University of Malaysia. My presentation title is Local Optimal Issue in Being Algorithm, Markov Chain Analysis and Integration with Dynamic Particles or Optimization Algorithm. This online or presentation, introduction and the problem statement, Markov Chain Analysis, the implementation of the integration to PSOA, and the comparison and the result. A bean cloning contains thousands of individual beans, but such a hit cloning can flexibly adapt to various living environments. They can allocate and divide tasks according to dynamic living conditions. Many researchers have established models for the intelligent behavior of bean clonians and try to use it to solve the current optimization problem. It's a brief timeline of bean algorithm. Shelley firstly established the self-organization model of bean clonians, and then many researchers continue to research on the intelligent algorithm related to beans behavior. And today, it's my pleasure to be here to do a presentation of BAA 2022 workshop. This table shows the optimization field of bean algorithm, such as continuous optimization and combinatory optimization field. It demonstrated that bean algorithm has wide application fields. This table shows the application and analysis of bean algorithm. It can be found that the bean algorithm has been integrated with some intelligent method to improve its performance. From our studies, we noticed there are two problems and solutions. A bean algorithm can fall into local optimal easily, and only a few studies using mathematical to analysis the convergence of bean algorithm. This is a detail of bean algorithm workflow. The first chart and the related parameters are shown on the right. Optimization algorithm usually need to solve its algorithm how to finally converge to the real global optimal solution, or how much probability to find the global optimal solution. Bean algorithm is a probabilistic heuristic algorithm. It combines neighborhood development search and global exploration search. The information exchange between all kinds of squared beans and fresh beans in each such iteration. So the whole bean cloning phase is very complex. The picture shows bean algorithm and Markov chain formalism based on mathematical method. It's trended from my paper. Equation 5 formulated the state transition probability based on the rule of squared beans. Equation 6 to 9 is one step transfer probability of the optimal and beta squared beans, where equation 10 to 11 is one step transfer probability of random squared beans. There are three theorems being used in the mathematical proof as shown from equation 12 to 19. From the perspective of such generative fitness, the fitness of a squared bean is defined as shown in equation 20, where the transition probability of the such state can be calculated by equation 21. According to previous studies, we can get equation 22 and 23. Then the gradient selection mechanism for analysis and the equation 24 and 25 were obtained as shown in the page. From the convergence analysis of bean algorithm, the site abandonment strategy can help the algorithm to escape the local optimal solution. To maintain the convergence performance, the strategy should be adjusted to discard food source that cannot obtain continuous improvement unless the food source has the current search of squared beans. If the best fitness is same, it should be stored in the current food source sequence rather than discarded. The adjusted site of abandonment strategy not only helps algorithm to escape local optimal solution, but also ensure that the search of the Scott bin converges to the optimal state mu with probability 1. In the previous slides, the convergence performance has been proved for Bin algorithm using Markov chain theory. However, without the site abandonment strategy, Bin algorithm is proven to be distributed in local optimal results. In this work, the combination model of Bin algorithm and DPSOA was attached to improve the local search capability by integrating the advantages of birth and Bin cloning foraging behavior. The optimization goal is to maximize the probability of Scott bin selecting tasks after the Bin algorithm global search. The DPSOA used for the Bin algorithm local search to solve the local optimization problem. The optimization in fact improved by updating the speed and position of the best bins, elect bins, and Scott bins, and iterating continuously until convergence. The first chart for the combination model of Bin algorithm and DPSOA is shown in the diagram. The DPSOA was used in this study based on sensitive particle. The feature is dynamic and is achieved by reasonably generated sensitive particles, and to start with each sub-search space divided evenly. The fitting value of sensitive particles is measured by the response threshold after the fitting value is calculated. The purpose of the combination model is that the Scott bin is allocated to the target allocation. To improve accuracy of the local search, the closer to the target, the better the result of task allocation. To verify the effectiveness of the method for task allocation of Scott bin, based on the combination model of Bin algorithm and the DPSOA proposed in this study, a simulation experiment was designed in MATLAB. The experiment parameters were shown in the table. The initial state is shown in the left diagram. Rosenberg function was used to test the computational model performance as shown in the middle diagram. A comparison, the algorithm performance was shown in the red diagram. We can find that the Rosenberg function value shown in the middle diagram was lower than the red diagram. The left diagram is the implementation result of combination method. As shown in diagram on the left, all points are get to the real target point. By comparison, there are few blue points are not get to the target point due to falling to local optimization as shown in the red diagram. This shows that it very well in the effect or task allocation of Scott bins or target allocation. The study can conclude that the probability of the combination model of Bin algorithm and the DPSOA falling to local optimization is much lower than the conventional Bin algorithm from the simulation experiment. This is our study conclusion. However, our study just analyzes the convergence of Bin algorithm and the DPSOA, but does not analyze other potential combination methods. And the setting of experiment parameters is only based on past experience. For the future work, we can consider more other combination methods and the experiment parameter setting. Thank you.
Hello dear engineers, the subject of this paper is Bees local phase quantization feature selection for RGB-D facial expression recognition. The authors are Signal Hussein Musabi and Atiye Imandi. As an introduction and for facial expression recognition, we can say it occurs after the face detection and face recognition. And we have FER and FMER, which are facial expression recognition and facial micro expression recognition. It's harder task relatively to face detection as it's involving micro movement differ from one person to another. Each expression could be misunderstood because of the spin wrinkles and races. and they are made of facial action coding system unit or FACS. They are categorized to 7 primary facial expressions of joy, anger, disgust, sadness, fear, surprise, and neutral. For example, for joy, action units are 6 plus 12. And FMER and FER with more precise calculation as a little change appears on the face. So, in the figure, we can see surprise, happiness, sadness, and anger, plus their action units. Bio-inspired algorithms, they are mathematical model of animal social behavior in a manner that leads to a problem to an optimal solution. These algorithms can be employed in multiple optimization tasks such as rotation clustering, feature selection, minimum span tree, application, allocation, and more. One of the best of them is Bees algorithm or BAA. This algorithm simply implements the social behavior of honeybees to search for food and flowers. Agents, scots, and foragers bees are involved in the global and local search for the best solution. Like a dance is done by scots which found the best sites. Those who landed on elite sites recruit new members. List of the best bees based on local and global goes to the next generation and suggests by termination criterion condition. The data is recorded with Kinect's version 2 sensor. It's cheap and it's good for educational purposes. The color data is 1920 by 1080 resolution, and the data is 512 by 424 in technical frame per second. Color data is RGB channel, and the data is a gray-like channel, which is called 2.5 dimensional images. For the gray images, each pixel of the Kinect sensor represents the distance between subject and sensor in millimeter. For example, 2000 value in pixel means object is in distance of millimeter from sensor. Depth image aids color and image to increase recognition accuracy, and as they are related to infrared particles, they can see or show objects in field darkness. For the feature selection is a useful in dealing with big data, massive number of samples, especially image data. After the feature selection happens, and it's good for selecting most impactful features out of data. Feature selection or dimension reduction help to reduce computational time and getting rid of outliers in data set. Outliers is to misclassification, so removing them is vital. So we are using this algorithm as a feature selection tool out of local-based quantization features. LPQ provides 256 features, and these feature selection selects less than 128 features without classification accuracy drop. These algorithms could be, now we are going to related research, the algorithms which could be directly applies on signal images or on an extracted version of them. So we have principal component analysis or PCA invented by Carl Pearson in 1901. Generate new matrix named principal component. So PA. Each PA is a linear mix of original matrix. By selecting best principal component, best feature will be selected. Another one is Lasso, which invented by Robert Shirani in 1996, is a regularization method for estimating generalized linear model. Lasso is shrinkage approximator. It makes coefficient approximated that are biased to be tiny. By shrinking feature, best feature remains, so be selected. The chi-square test by Jin 2006 is another feature selection method and a statistical method employed to contrast observed data and expected ones. The objective is to specify if there is any change between observed data and expected one. If the target variable is independent of feature variable, it is possible to ignore the specific features. If they are dependent, the feature is very significant, so they will be chosen. Imported by inspired feature selection, peers of Ergonomic and these algorithms are best. This is our proposed method. So it's a static data acquisition with data input from IKFPD dataset. We have processing step, then extracting LPQ features, then selecting this feature out of LPQ features, labeling them for supervised learning, classification with different algorithms, and comparing with different other methods. Finally, conclusion on matrix and RGB for plots. Local-based quantization on LPQ is a frequently neighborhood-based feature based on Fourier transform. It manipulates blurring effect in magnitude and phase channel. Phase channel is capable of deactivating low-pass filters that exist in some images, like the image which we are going to use. LPQ feature is perfect to be used on depth data in frequency domain, and in the figure we can see the process of LPQ image on LPQ feature on image. So in this feature selection, number of features, weight of that feature, and MSC or mean square error of that feature is important. The MSC should be minimized, so those who have the less error would be selected. So if we have xi values of a number of features, and xi hat would be selected feature out of NF. So considering number of features entering the system, y would be the output and t would be the target. So the difference between the output and target would be our error. In order to calculate the final error, need to be calculated, EI need to be calculated, which is ti minus yi. So the final error is MSE plus weight of the feature multiplied by number of features. This goes for all features, and finally those features with the lowest MSC will be selected. In combination of these as feature selected, each feature vector is considered as a B with a different fitness function. Those with B's which could fit into final iteration will be selected alongside with their related feature with lowest error as it mentioned. Here we can see the pseudocode of this feature selection. I'm not going to explain it. It start too much. Just start with LPQ features and population generates and fitness function and weights of each feature. Then we have some sorting. Then it is there is a while for iterations, and finally those B's which they have after each sorting, we select a number of features out of all features, and the best of those selected features, for example 10 best or 120 first best, will be selected as the features. Our data is IKFPD or Dynamic Net-Based Database, which is runs the seven main facial expressions. There is 1,000 of color images are selected out of this database within 5 expressions, each 200 samples. Comparison is with Bees LPQ, PSO LPQ, PC LPQ, Lasso LPQ, and Solo LPQ. SVM, KNN, shallow neural network, and subspace KNN are used for this purpose. Here we can see some samples from this database. Validation, as we can see here, there are Bees and PSO algorithms which are used for comparison, so the parameters are clear, almost the same, except Bees algorithm use 10 population, PSO use 20. Here we can see the result achieved for all classification and all algorithm feature selection. LPQ uses all the features, so 256 features are used. PCA, Lasso, PSO, and Bees are using half of the features, a quarter of the features, and half of the quarter of the features. So 128, 64, and 34. Here we can see this algorithm has the best performance, then we have PSO best performance, then we have all the data with LPQ, then we have PCA, and final place is for Lasso. Some figures for confusion matrix and RGB here we can see for LPQ, Lasso, and Bees. For SVM, LPQ is all the features, and Lasso 64 bits, Bees and 64 bits. The best is Bees, then we have LPQ and the worst is Lasso. The same is for KNN here, we can see. Again, Bees is the best, LPQ is the second place, and Lasso is the third place or last place. Here we can see some iterations from this feature selection algorithm. As we can see, the convergence happens in 50, the iteration number. So as a conclusion, we can say employing volume-spared algorithm for feature selection task could perform better than traditional feature selection algorithm in phase analysis. Defining feature selection cost function for these algorithms returns successful result for all classification algorithms. It can be concluded that these algorithms have great impact in feature selection optimization. However, runtime is increased, but as the training and learning is for a model is just one time, there is no specific problem. These algorithms with using just a quarter of feature could reach to a point which traditional algorithms are not capable. Using proposed method on more facial expression and in other face analysis tasks such as face recognition is of future work. It's suggested to use proposed method with more classification algorithms like freeze, Bayes, and even more. Also, it is suggested to compare with more traditional and volume-spared feature selection techniques such as Fisher and directed algorithms and more. Here we can see some references, all of the references which are used in this experiment and research. So thank you so much for your attention.
In this presentation, I'm going to introduce our work on combined grasp pose and joint motion optimization for robotic 3D pipe assembly manipulation. First, let me introduce some background of this work. This work stems from an industrial project called Factory in a Box. The aim of this project is to build a compact factory for manufacturing pipe assemblies. The main features of the factory are mobility and flexibility, which means the factory can be deployed rapidly at different places, and it can manufacture pipes of different geometries and dimensions. After receiving orders from customers, the system will perform simulation to check if the required dimensions of the pipes are feasible to manufacture. If the simulation is successful, the actual manufacturing process will start. The manufacturing process involves cutting, bending, brazing, and pressure testing. As we can see from the picture, an industrial robot is mounted on an overhead rail to move the pipe between different manufacturing operations. Currently, the system requires specially designed gripper for grasping the pipe. The specially designed gripper is robust. However, as you can see from the picture, it is also large, heavy, and expensive. In addition, the size of the gripper may constrain the motion of the robot, the choice of grasp pose, and the geometry of the pipe. Therefore, a natural question to ask is whether we can use a low-cost and general-purpose two-finger gripper to achieve robust and efficient robot motion. Fortunately, the simple cylindrical shape of the pipe section makes it easy to grasp the pipe. However, we cannot grasp anywhere we like, because some grasp pose may lead to axial deformation of the pipe, while others may introduce unavoidable collision. Therefore, we need to carefully optimize the grasp pose as well as the joint motion. In this work, we assume the trajectory of the object being manipulated is predefined and given as a series of waypoints. Therefore, the research question becomes, given the geometric trajectory of the pipe in 3D space, how can we find the optimal grasp as well as the joint motion for the robot to manipulate the pipe to follow the trajectory? Here, the joint motion are only planned on the geometric level. That is to say, no velocity or acceleration is considered. In order to optimize the choice of grasp pose, first, we need to have a valid representation of the pipe geometry for generating grasp pose. The grasp pose is also the decision variables of our optimization problem. Although a general grasp pose requires 6 degrees of freedom, In our case, we can use only 4 parameters to represent the grasp. The first parameter is the grasp section. For example, S1, S2, and S3. This one parameter actually defines 2 position variables, and we only need 1 additional variable to fully define the grasp location, which is the length between the start of the pipe section and the actual grasp location. The orientation of the grasp pose is defined by the grasp angle phi, which is this angle here, and the flip angle theta. So as you can see, the flip angle can only be 0 or 180 degrees because of the constraint of the geometry of the pipe. Now we need to introduce the constraint and the objectives of our optimization problem. The first constraint is the trajectory of the pipe must be followed exactly. The second constraint is that there is no collision allowed between robot, pipe, and the environment. There are also 3 objectives. The first objective is to minimize the distance of robot joint motion. The second objective is to minimize the deformation of the pipe. In order to compute this objective, we have developed a custom finite element program specifically for pipe structures. However, it is also possible to use external torque on the robot wrist as an alternative objective. The third objective is to minimize the force manipulability. This is because minimizing force manipulability is equivalent to maximizing the velocity manipulability, which means the robot can generate a faster in-effect motion. Now that we have defined our optimization problem, it is time for us to choose a suitable method for solving the optimization problem. In this work, we choose Bees algorithm. The reason that we choose Bees algorithm is it can incorporate both discrete and continuous variables. In addition, you can also explicitly control how many global searches you want in each iteration, which is very important for jumping out of local minima. In terms of constraint handling, we first evaluate whether the solution satisfies all constraints, and then only compute the objective for feasible solutions. This is beneficial since the deformation objective is very expensive to evaluate. We use weighted sum to combine 3 objectives and the analytical hierarchy process to determine the weight. You may have already noticed that we said we want to optimize both grasp pose and the joint motion, but we only use grasp pose as decision variables. This is because each grasp pose usually has a finite number of inverse kinematic solutions for a non-redundant robot. Therefore, the problem of optimizing joint motion becomes solving inverse kinematics problem and followed by a shortest path search on the robot configuration graph, just like the figure here. An important step of the Bees algorithm is the local search strategy. However, using the parameterization we introduce, it is difficult for standard Bees algorithm to generate solutions that are close in terms of Euclidean distance. Figure A is an example here. The local neighborhood on S1 is actually far from the solution set, which is the red star here. Therefore, we introduce 2 problem-specific local search strategy. The first strategy is to constrain the local search neighborhood on a single section. However, this strategy turns out to be too conservative. The second strategy is to consider the geometry of the pipe and extend the neighborhood to the section next to the current solution set, which is as shown in figure 3. This method actually provides the best overall performance. as we'll be showing next step. So these are some benchmark results. We benchmark the proposed local search strategies against other meta heuristics. That is to say, genetic algorithm and particle swarm optimization. This is the result, and as you can see, STR3 achieves the highest success rate in finding the optimal solution with fewest grasp evaluations. We also compared the result of whether using multiple IK solutions or only consider single IK solutions, because not every robot has analytical IK solver that can generate multiple IK solutions very fast. So the red line is using multi-IK solutions, and the blue line is using only single IK solutions. As you can see, the difference is significant, which suggests that we should always consider multiple IK solutions whenever it is possible. Okay, thanks for listening. Now I'm ready to take questions.
Hi, everyone. I'm glad to present the work entitled Surrogate Model-Assisted Bees Algorithm for Global Optimization of Microwave Filter. Microwave filter is an important class of electronic components in modern wireless communication and radar systems. It aims to select, separate, or combine different electromagnetic spectrum. As shown in Figure 1, the 3D shape of the microwave filter is parameterized by physical dimensions, and only the electromagnetic wave in the passband in frequency domain can pass the filter. The design procedure consists of 4 steps. Given design specifications, work out the circuit or the coupling model, extract the initial dimensions or real filter structure, and finally optimize the filter physical model. The last step is an optimization problem. The initial geometric parameter is not ideal as shown in the Figure 2. It requires a simulation-driven shape optimization process. This optimization problem is characterized as a black box optimization. There are 4 challenges. First, multi-dimensional solution space, the well-known curse of dimensionality. Second, multimodality, that means there are many local minima. Third, unknown objective function. The objective function relies on a black box electromagnetic simulation. Fourth, the EM simulation is computationally expensive and time-consuming. It costs 1 minute to 10 minutes or even longer. This work proposes Bees algorithm with surrogate model assistance for microwave filter optimization. The motivations are twofold. First, improve global search capacity. Second, exploit data efficiency as EM simulations are very precious and expensive. The Bees algorithm performs as a global search mechanism and intelligent sampling for surrogate modeling. The surrogate model using Gaussian process learns the landscape of the solution space with uncertainty, as shown in Figure 4. It can predict the unseen areas to substitute EM simulations. Data efficiency is addressed by pre-screening. The method integrates the Bees algorithm framework with the surrogate modeling and pre-screening. As shown in Figure 5, before local and global search, the training dataset is updated, followed by surrogate modeling via GP. The approach enters local and global search with pre-screening. As shown in Figure 6, in local search, for each forager, C candidate bees are generated and predicted by GP prediction. The best candidate bee is selected for cost evaluation. The pre-screening step is repeated until the fittest bee is obtained for the site. The global search performs the same strategy for pre-screening. C times the number of scout bees are generated for pre-screening. On the top, the number of scout bees are sent for EM simulation. The experiment tested the approach on 7 benchmark functions, including 2 unimodal and 5 multimodal functions. The algorithm is parameterized as follows. The solution's dimension is set as 10. The Bees algorithm and Gaussian process are set for the remaining tests. For each benchmark function, the algorithm performs 20 runs. The box plots are shown in Figure 8. The y-axis is in logarithmic scale. For the 2 unimodal functions, ellipsoid and sphere, the GP-assisted BA obtained extremely low cost values compared to the standard BA. For the remaining 5 multimodal functions, the GP-assisted BA reduced the cost values significantly, showing improved global search capacity. The Mann-Whitney U-test shows all nearly zero p-values for all functions, which verifies the statistical significance of the results. A dielectric microwave filter is tested as a case study. The 3D model is presented in Figure 9. It has 6 parameters. In Figure 10, the red curve is the S parameter for the initial dimensions obtained from design procedure. It's far from the ideal as shown as the black curve in Figure 10. It's not practical for manufacturing and requires optimization. The cost function is defined according to the specification. It has 3 components. The first part, E0, is the maximum value in passband. The remaining 2 terms are penalties. Lambda is set empirically to 25. Figure 12 shows the cost curve during optimization process. The genetic algorithm provided by CST software is not able to generate a good solution. The cost value remains very high. The standard BA optimizes the cost value, but difficult to fulfill the specification that the cost value should be less than -20. The GP-assisted BA addresses data efficiency and reduces the cost to -20 using 84 cycles. In Figure 13, the 3 algorithms align the central frequency of the passband of the S parameters. The green curve denotes the genetic algorithm, which has a very poor performance in passband. The blue curve denotes the standard BA. It has a good S parameter in passband. However, the maximum value in passband is not below -20 dB for industrial purpose. The red curve denotes the GP-assisted BA. It satisfies the specification in both passband and stopband. It's very close to the black ideal curve. The maximum value in passband is below -20 dB, indicating that it's practical for industrial application. In conclusion, this work addressed the 4 challenges for microwave filter optimization. This study proposed the Gaussian process-assisted Bees algorithm. The Bees algorithm performs as global search and intelligent sampling. The surrogate model pre-screens the candidate bees. Finally, the results show the proposed approach improved data efficiency, global search capability, and fast convergence. Here lists the references. Thank you for your attention.
Good morning, everyone. I'm Aditri, and together with Anubhav and Satya, I'll be presenting our work on the topic Utilizing the Bees algorithm to optimize the UAV path planning to avoid collision that we have been working on under Russell Sir. So let us dive right in and first discuss the problem at hand. The unmanned aerial vehicles, popularly known as UAVs, have been used for various dangerous and difficult tasks for a very long time. In the recent years, however, this vehicle has also been utilized for trivial human conveniences like deliveries. Automatic path planning is a crucial component of UAVs, and given its rapid shift to usage in human habitats, a safe and efficient path planning method is a critical need of the hour. The problem can broadly be divided into 2D and 3D environments, each having two subcategories of single and multiple UAVs. This presentation largely focuses on our work on the 2D single UAV problem, following which we shall also present some of our ideas and plans for future work on 2D multiple UAVs and the 3D single UAV problems. The state-of-the-art methods being used in this domain can broadly be divided into four categories as shown. When we try to compare and critique these diverse set of methods, the first question that came to our minds was, what is the metric to judge the performance of these algorithms given the context of UAVs and the environment that these methods are going to function in? The most obvious metrics that might be occurring to you right now could be things like lesser fuel consumption or lesser distance traveled and so on. However, the most important metric is the response to dynamic environments. An algorithm that gives you the shortest path but fails to identify an obstacle and leads to a collision is always worse than one which may have cost you some more fuel but at least completed the task safely without any collisions. That being said, here's a clearer picture of the hierarchy of metrics based on their relative importance. First up, we have dynamic response. Secondly, we have the ability to always give us a solution instead of being stuck in a local minima. And thirdly, we have further optimizations. Thus, we first try to find a domain of methods that satisfies the first two criteria. So now the graph search algorithms and the sample-based planning approaches always require prior knowledge of the system, which is often not possible to obtain beforehand, thereby giving the other two set of methods an edge over them based on the primary metric. Coming to the secondary metric, a major drawback of the potential field methods is its susceptibility to local minima. Another one being the inability to find a path between two closely placed obstacles. Even the modified versions where these issues are taken care of, the direction of motion can get difficult to decide upon. All in all, it may not always give us a solution. And thus, the problem now boils down to comparisons among evolutionary algorithms that Satyam will be elaborating upon.
We not only integrated the two-parameter version of Bees algorithm, but also the basic version of Bees algorithm with our problem setting. We then compared our algorithm with other evolutionary algorithms while keeping in mind that everything in the environment, including the initial swarm population, was exactly the same as the other algorithm that we compared our results with. Now moving on, I'll be talking about the cost function and the comparison metrics. Firstly, we made sure that the cost function used in calculating the cost is identical with that of the article wherein Grey Wolf Optimizer had been used for similar problem. The cost function that has been used in our work contains an economic cost term as one of the parts, which basically tries to reduce the fuel usage and takes an obstacle avoidance metric as the other part, and together both the parts are weighted to create the required objective. Dummy points are constructed in between the consecutive pairs of waypoints so as to approximate the integral calculation of the cost function and to make it easier for the computation. Here you can see the table where we have used namely three types of parameters, which are thread centers, thread radius, and thread grade. So these parameters were used to compare our two-parameter version Bees with all the other evolutionary algorithms. Now moving on, this is the flowchart which represents our integrated algorithm for computing waypoints for the UAV in 2D using 2-parameter version of bees. As you can see that the entire optimization is being performed across 3 loops. This is the main part of our 2-parameter version of bees algorithm. Next, we move forward to present our results. This is the result that we obtained from basic bees. It shows the cost function with the number of iterations and also the planned path. Now I'll be showing you the result obtained from 2-parameter version. This is the result that we obtained from 2-parameter version of bees algorithm. This one shows that the cost function is way much lesser compared to the cost function obtained from basic bees. And even the planned path is much more optimized and much more efficient compared to the basic bees, which clearly suggests that the 2-parameter version of bees algorithm is way better than the basic bees algorithm. Now there are several evolutionary algorithms that we have compared our optimized bees algorithm with, and the result has been formulated in a table which will be presented in the next slide. Here is the comparison table where I'm sure everyone can clearly see that we are comparing using 4 metrics which have been obtained after carrying out 30 runs with 10 different waypoints. Here we have taken the best cost, the worst cost, the mean cost, and the standard deviation of the cost as the metrics. As it has been clearly highlighted that the 2-parameter bees algorithm performs better than the rest of the algorithms. This justified the efficiency of 2-parameter version of bees in being used for path planning for UAVs in 2D environment. Next, I would like Anubhav to talk about some of our major findings, our future works, and the formulation and ideas for multi-UAV path planning problems.
So we just saw the results and how BA2 performs better when compared to basic BA and also some other algorithms like GWO. There are 3 main reasons as to why that is happening, and the primary reason is that in any evolutionary algorithm, the exploration strategy should be strong and relevant to the problem. In our case, we have a function defined over the 2D Cartesian space, which makes the environment easier to explore than functions defined over some abstract or graph-based environments. BA2 uses a radial exploration strategy to update the waypoint positions, which is better when compared to GWO, since radially exploring will follow an unbiased distribution. Next is the fact that BA2 also implements site abandonment based on a stagnation limit, which prevents the buffer from getting too heavily packed with data and also keeps the optimization process free from getting biased by search locations, which won't improve the cost. Lastly, BA2 also implements neighborhood shrinking by not letting the waypoints change too much or to allow it to change over a certain restricted horizon, which further adds on to the exploration becoming more fruitful. In the future, we look forward to expanding our work by formulating the 2D multiple UAV path planning problem such that we can use BA2 for optimization but at the same time keep the computational complexity reasonable. Because multiple serial optimizations followed by intersection detection will be computationally very extensive. We also hope to utilize publicly available 3D datasets for expanding our path planning work in a 3D environment. Here, we propose our approach for the 2D multiple UAV path planning problem, where we would proceed by utilizing the patch buffer which stores the waypoint data and by picking up as many ranked patches from the buffer as the number of UAVs. This will be followed by a correction step to remove intersections between chosen trajectories following a sequential search approach. Then we recalculate the costs after updating the patch buffer and continue with the optimization. Our main point being that the correction step and the optimization step will soon start reinforcing each other with the increasing number of iterations, and the buffer will start getting structured in a manner which will provide us with non-intersecting trajectories when we select the patches. With this, we come to the end of our presentation. Thank you, everyone.
It will be based on utilizing the Bees algorithm and implementing machine learning to optimize the UAV's travel time in consideration of the weather conditions. So me, Vedant Zope, Susnata Biswas, Deepshika Behra, and Asrul will be working together on this project. So I'll go on and introduce to you about this thing. So during this past few years, the development in unmanned aerial vehicles and their use in different fields has been on rise. While they have been proven very effective in aiding relief by delivering emergency kits in the affected areas, the use of UAV for more day-to-day purposes like package delivery has become a flaming topic. While majority of the other research scopes only focus on dealing with routing, payload, and surveillance, weather conditions also play a very massive role in UAV's efficiency as well as their safety in real-world application. Hence, our research will majorly go on and talk about the UAV's application in weather conditions, and it is also very essential to pay special attention to all these factors that influence the deployment of UAVs in these various conditions. So we'll start, I'll go on and explain our approach to the model. So first we started with looking at the weather data and started analyzing the weather parameters, that how the weather parameters affected the total duration of the UAV and how they affected the UAV speed. So when we went through a lot of data, we saw that there were a lot of weather parameters that affected the UAV velocity. But when we narrowed it down, we saw that wind speed, wind gust is basically short burst of wind speed, and wind direction had a very major effect on the UAV velocity. So we'll be going to use these parameters along with the other UAV parameters to predict the final UAV velocity. And then we are going to use combinatorial Bees algorithm for routing optimization. For routing optimization, for now, we are using the traveling salesman problem, where the salesman could represent the drone and the cities could represent the delivery locations. Now I'll say this, that this problem classifies as asymmetrical traveling salesman problem. As well, considering the weather conditions, the time from node A to node B may not necessarily be same as the time from node B to node A. Now, we worked with weather parameters and developed a model to accurately predict the final velocity. We worked with various machine learning models, including polynomial regression, XGBoost, LightGBM, and we also worked with artificial neural network as a deep learning model. But we found that CatBoost, which is a boosting based ensemble model, performing a lot better than these other models, and we got a MSE score of 0.58. So for the routing optimization of the UAV travel path, we are using the combinatorial Bees algorithm. Although the accuracy and better prediction of UAV velocity is not our exact aim, we should keep that in mind. The optimization technique can correctly predict the time fluctuation during weather turmoil, and the UAV velocity also plays a very important role in the total duration. Hence, it is necessary for us that we accurately predict it. While the basic combinatorial Bees algorithm works on the basis of Euclidean distance, which is stored in a matrix, and the total distance of the Hamiltonian cycle is minimized using the optimization algorithm, our study is a bit different than that and will be considered as a modification to the combinatorial Bees algorithm, where it is not necessary that the shortest distance will be the fastest. Hence, we will be majorly working on minimizing the total duration of the journey. Now here is the pseudocode of our working model. So we'll start with the D, which will store the total duration of from node A to node B, and we'll be considering weather parameters and other UAV properties. On the basis of that, we'll predict the UAV velocity between node 1 and node 2, and then append it to the duration matrix. Now I'll visually go on and explain how this works. So this is a model where we have considered 5 nodes, and a distance from a node is defined, and the time taken from the node 0 to node 1 is A hours, whereas I've defined a nomenclature where the time from node 0 to node A is A, and the time from node A to node 0 is A dash. This is the reason that I explained before, that I'll classify this as a asymmetrical traveling salesman problem, as the distance, as the time taken from node A to node B is not necessarily the same as the time taken from node B to node A. Now the total our objective of the total work has been reduced to minimization of a optimization function that we have found, which is the total duration, which comes out as the summation of the time taken by the drone to move from all the nodes so that all the nodes are covered and a complete cycle is formed. This is a flowchart of how our works goes on. We start with pre-processing the dataset and splitting the dataset. Then we go on to rank our machine learning models, which predict the UAV velocities, and the trained models are then combined with the best trained model are combined with the combinatorial Bees algorithm, which are used for the routing optimization of the drone. Now, how the Bees algorithm works is it starts with initialization of the scout bees and the number of iteration. Now, at the very start of this workshop, Mr. Adams talked about how it is very necessary for optimization algorithm to be very useful. It is necessary for optimization algorithm to have less parameters so that it can be easily deployed. So we start with number of scout bees and number of iterations which we have handled using our experimental results, which will be talked about in the later parts of the slides. So we just have to start with the initialization of the basic scout bees, which then go on to evaluate the fitness of the solution, which is done on the basis of the cost function. And then the local search and global search is performed, which is iteratively used, and when the current best cost function is greater than the least cost function, we have found the best model, which goes on iteratively, and using hill climb we find a solution which is very close to the optimal solution. It may not necessarily be the optimal solution, but yes, we have found a very solution very close to the optimal solution. Now my friend Susnata will go on and explain about how we'll be handling the number of iterations, and then talk about our further plans.
Thank you, Vedan. I am going to explain for the later half of the parts. So here in the next slide, we have figured out an experimental result to deal with the number of iterations, which may be handled using hypertuning on these algorithm parameter. But it may be costly and time consuming approach. Sometimes we should come up an experimental result by visualization or finding a trend rather than going for an experimental tool. We have applied our optimization approach for different data set like EIL51, Berlin 52, ST70, EIL76 and RAT 99. Here we are showing our result only for 3 data sets. The observation we have got is for almost all the data sets are same. Our result is converging at a fixed number of iterations. Approximately, this algorithm attains its saturation point at a iteration number of 3 times into number of data points present in the respective data set. For example, number of points x, y present in EIL51 is 51, and the convergence occur at a iteration level is approximately 150 around. So we need to handle the number of iteration effectively, as the less number of iteration may result in a suboptimal solution, whereas more number of iteration may result in unnecessary increase in computational time with no significant change to the solution. So hence we need number of iteration which is computationally fast, and we get an optimal solution at the same time. Can you move to next slide? So in this slide, we are mainly explaining the result and the discussion which somehow overcomes the problem of time lags in UV path optimization. We have already explained the approach of a solution. So basically, I am trying to explain the scenario with an example of test case. We are considering a constant weather condition like UV speed around 25 meter per minute, UV payload is 15 kg, wind speed around 10 meter per minute, and wind gusts is around 5 meter per minute. And the direction is along to x-axis is 65 degrees. Initially, we are not taking care of weather impacts on routing, and the total time taken to complete the whole journey is around 32 minutes, as you can see in the slide. But in our optimized approach, is come down to 24 minutes. That is around 25% reduction in travel time. Here, the wind is helping to complete its mission. Maybe in another parameter of weather, it will not affect. It will not. So our main aim is not always to reduce the travel time. It is more about to accurately predict the duration so that scheduling things can work efficiently. Thank you.
Good morning, everyone. My name is Abhijit Singh, a second-year undergraduate student of the Department of Computer Science and Engineering at Indian Institute of Technology, Kharagpur. I am going to make a presentation on a research paper, Ergonomic Risk Assessment, combining Bees algorithm and simulation tool. This research paper includes myself, Dr. Catrino, Dr. Renald, include introduction to a research topic, methodology, case study, results and discussion, conclusion. First, we'll proceed with the aim of our research. Our paper is titled Ergonomic Risk Assessment, combining Bees algorithm and simulation tools. Some key terms for our research is job rotations, which means rotating heterogeneous workers among workstations. Physical ergonomic risk, which means risk of developing occupational disorders. This may be due to factors such as awkward posture, forceful motion, etc. Ergonomic risk assessment, which means using simulation tools to create ergonomic risk-based different heterogeneous. So in our research, we are trying to minimize the overall ergonomic risk, considering postures for an assembly line consisting of 6 workstations. We have used Bees algorithm to find the solutions, and we have considered heterogeneous workers with different anthropometric characteristics. So why this research? The methodology for this used in this research can help in reducing physical ergonomic risk of the workers, thereby greatly reducing WMSDs, work-related musculoskeletal disorders. It is one of the most commonly related work-related health problems. It also causes serious medical condition leading to chronic pains or even permanent disability to the worker. It even leads to absenteeism, thereby decreasing the operational efficiency of the factors. It also decreases individual workers. The cases of WMSDs exceed 1,000 per 1 lakh workers. So it is a very serious problem, and we are solving this problem by this research. So the research framework for our research is in the first step, we do the system analysis in which we find the cycle time of each task and ergonomic risk factors which contribute to the WMSDs. Then we, with the help of simulation and the data obtained from system analysis, we do the ergonomic simulation. From this, we get digital twin and simulation. With the help of digital twin on anthropometric data and sets of workers, we get the ergonomic risk assessment, where we get score for each combination of worker and workstation. We apply Bees algorithm for job rotation on this score to get a best score for each configuration, score for each job rotation test, and worker to workstation configuration. Then then a simulation is generated by reproducing workstations in digital environment. The data related to movements and working actions are implemented through digital human modeling. All movements needed to feed into the software once. Software automatically adapts to the posture depending upon the sex and anthropometric characteristics. In the left, we can see a picture how we are inputting the anthropometric characteristic into the software. Based upon the task to perform, the software creates various postures according to the type of workers. These postures determine the value of ergonomic indices. So we have used basic Bees algorithm for this problem, and this is a flowchart depicting this, where we first do the random initialization followed by fitness evaluation, and based upon the results of the fitness evaluation, we do the local search on elite site and best site followed by global search, and the answers from the local search and the global search is added into the new population. And if the stopping condition is not met, the process continues. Otherwise, we get our final solution. So we have considered 6 workstations. The work done at the various workstation is described here. At workstation 1, we grab and carry the central locker and assemble it at the left side of the locker. At workstation 2, right side of the locker is assembled. At workstation 3, lower steering guard is assembled. At workstation 4, left and right side screwing is done. At workstation 5, left seat belt rod is assembled. At workstation 6, right seat belt rod is assembled. These are few pictures of the pictures generated by the simulation software of various tasks being carried out. So we have used OS index for our research. OACO working posture analysis system method has been used to assess awkward posture. It classifies the work posture for each body part in terms of back, legs, and head. On the bottom right, you can see a picture which depicts it is a 4-digit number. The first digit in this case is 4, which is for back, which shows it in high risk. Similarly, the arm is in medium risk, the legs is in high risk, and head is in low risk based upon the number generated by OS. So below you can see the formula for the OS, calculating OS, which is A into 1 plus B into 2 plus C into 3 plus D into 4 into 100. So this generates a value on which we can classify the risk, the category of risk. If the value comes out to be 100, it is no risk. If the value comes out between 100 and 200, it is low risk. If the value comes out between 200 to 300, it is medium risk. And if the value is between 300 to 400, it is high risk. And so this is a chart containing of the anthropometric characteristics of the 10 different types of workers which we have considered. This is a data related to OS values for different anthropometric characteristics and different workstations. So you can see the variation of OS index value even for the same workstation between different workers. It shows the necessity of job rotation to reduce the physical ergonomic risk. This is also those values. So on the top, you can see an objective function which we have minimized for this problem. So we have used Bees algorithm mainly due to 2 reasons. Execution time is greatly reduced and error percentage is very small and almost negligible in some cases. A demonstration of how execution time is greatly reduced is shown by the table below. We can show that for 2 job rotations, the Bees algorithm takes 0.48 seconds for 200 iterations, whereas exact solution takes 137 seconds. For our problem statement, we were able to generate exact solution also, but when we increase the number of workstations from 6, this will not be possible. So these algorithm becomes important, and it also generates the result in quite less time. So in the results and discussion section, we compare the effect of increasing the scout bees on the error percentage between the solution generated by Bees algorithm and the exact solution. So at 20 scout bees, this error is around 0.19%. At 30 scout bees, this error becomes 0.13%. And at 50 scout bees, this error becomes 0.05%. The number of job rotations for this case considered was 2. And in this table, we consider the change in error on increasing the number of iterations. The number of scout bees considered for this case is 20 and number of job rotations 2. On 50, a number of iterations, 50 iterations, the error is 0.42%. At 200 iterations, it becomes 0.15. At 1000 iterations, it becomes 0.06, gradually decreasing with increasing the number of iterations. So this is a graph in which we have considered 3 different number of scout bees, and we have continuously increased the iteration from 1 to 1000. We can see that at above 800 iterations, the yellow line, which is for the number of scout bees 50, almost starts to disappear, which means it has collided with the exact solution. At 200 iterations, the error between by the algorithm and the exact solution becomes very less. So this can be the findings from this graph. So this is a worker to workstation configuration for 3 different job rotations. For job rotation 0, the worker 1 will be at 3, worker 2 at 5, and similarly. And for one job rotation, worker 1 will be at workstation 3 and workstation 2, worker 2 will be at workstation 6 and workstation 5, and so on. And for 2 job rotation, this will be worker 1 will be at workstation 3, 6, and 5, worker 2 at workstation 6, workstation 6, 5, and 2, and similarly so on. The workers considered for each of these configuration was the 3 female 50 percentile, female 75 percentile, female 95 percentile, male 5 percentile, male 25 percentile, and male 50 percentile. So the conclusions from our study is, for sure, the Bees algorithm was very effective in analyzing and reducing the ergonomic risk. Bees algorithm was also very fast and accurate, and in some cases, it was almost giving the exact solution. The limitations of the study include, in our study, we have considered only one ergonomic index, which was OS index. We have only focused on minimizing the sum of OS index of all the workers and not tried to minimize the individual OS index of all the workers. And so this brings to our scope of further development. So we will try to include energy expenditure in our study, and we will also try to minimize a multi-objective function comprising of both energy expenditure and OS index. We will also try to find the most balanced configuration where OS index of different workers are better balanced. So thank you. This was Abhijit Singh signing off. I am now open to questions.
So our project is about optimization of a fuzzy logic controller for a robotic arm using 2-parameter Bees algorithm. Coming to the introduction part, firstly, we should know what is a robotic arm. So since the beginning of the evolution of robots and its use in industries, robots have been used for locomotion purpose, but apart from locomotion purpose, they are also expected to have an arm movement to carry goods or place them at required positions. In industries like manufacturing industries or packaging industries, or if we talk about automobile industries, when the robots are required to manufacture something, they need robotic arms to place the goods at required position. So we require a good robotic arm for fulfilling these purposes. Now, to control any robotic arm, we have different control algorithms as well as control systems. But in our project, we'll be dealing with the fuzzy logic controller and how we can optimize it using 2-parameter Bees algorithm. So, coming to the factors which decide efficiency and reliability of a robotic arm. Firstly, the accuracy. The robotic arm must reach the desired position with minimum possible error in position. That means that a robotic arm should reach the position that the controller wants, and it should have minimum error in reaching that desired position. And when this accuracy will be high for a robotic arm, then only it will be useful. Second factor which plays a major role is speed. A robotic arm must be quick in taking response. It must reach the desired position as fast as possible. The third important factor which plays a major role is vibrations. A robotic arm must have minimum vibrations during the motions, and its motion should be smooth so as to carry goods. So for optimizing these 3 parameters, we are using a fuzzy logic controller. And then we'll further improve this controller using the 2-parameter Bees algorithm. Now coming to the proposed approach for our problem. Firstly, we'll be modeling a fuzzy logic controller using MATLAB and Simulink. And we'll be using all the necessary components that a fuzzy logic controller has. And we'll just create them using MATLAB. Secondly, we'll use a 2-joint robotic arm, and it will also be modeled using MATLAB. And the last part of our project will be optimizing this fuzzy logic controller by using 2-parameter Bees algorithm. In this part, there will be 48 variables which will be optimized. 3 are the scaling gains, 15 are for the 2 inputs that we are taking for the controller, and 15 for the output. And after getting the results, we'll comparatively evaluate whether the performance of the robotic arm has enhanced or not. Coming to the fuzzy logic controller, to give a basic idea about what it is. Fuzzy logic controller uses fuzzy logic. That is, it eliminates the extremities that our binary logic has. We will use two input parameters and it will give one output parameter. The two input parameter will be the error in position and the error in angular velocity. Each parameter corresponds to two triangular membership function consisting of 5 input parameters. So we'll be using two triangular membership functions for each input parameters for making it a fuzzified, for giving it a fuzzified set. The rule base will consist of 25 rules. After getting the fuzzified input from the fuzzification block, we'll use this set of 25 rules to get the output. So below are the images of the membership functions and the graph that we'll be using. Coming next to the model, what the entire model has. In step 1, we'll be taking the crisp inputs from the process that we will be controlling. In our case, it is the robotic arm. We'll take the crisp inputs and feed it into the controller. The inputs will be the error in position that we are getting and the error in angular velocity. After feeding it to the fuzzy logic controller, there will be a fuzzification module which will take this crisp values and will convert it into fuzzy sets using the membership functions that I have already shown. Both the membership functions will be used to convert these crisp values into fuzzy sets. Then the fuzzified inputs will be fed into the interference engine, which will use fuzzy rule base to evaluate the output, which is again a fuzzy set. Those 25 rules will be used to carry out the necessary options, and the output will again be a fuzzy set, and this fuzzy set will be passed to defuzzification module, which will again use another membership function for converting this fuzzified sets into the crisp value, output crisp value that will be fed into the process. In our case, that is the robotic arm. Coming to the approach of applying Bees algorithm in our model. So we will be using a 2-parameter Bees algorithm, and I have mentioned the reference for this. So to implement it, we will be adding another block for modifying the membership functions. In our case, this block will have the code that will be based on the 2-parameter Bees algorithm, and it will firstly modify the 3 scaling gains, namely K1, K2, K3. These scaling gains are used to transform the crisp values into range of -1 to 1 so that we can apply membership function over them. So firstly, we will optimize these 3 values, K1, K2, K3. They are scaling gains. Then we will be optimizing 15 parameters for membership functions. We have 5 parameters for membership function. According to the error that we'll get from the input, we will be classifying it into 5 types. That is large negative, small negative, 0, small positive, and large positive. So there will be 5 parameters, and totally it will be 15 parameters for 2 input parameters and 15 parameters for the output. This is how we will be implementing the code. So in our case, in simple fuzzy logic controller, it uses a triangular membership function, which is a isosceles triangular membership function, but we will be optimizing it by changing its shape. So each B will contain 3 parameters, that is A, B, and C, which is shown in this particular diagram. Then we will go for global search, and then we will rank and select the patches. In this 2-parameter version of Bees algorithm, recruitment and assignment will occur. And in this version of Bees algorithm, more promising site will receive more worker bees, and neighborhood search radius will be determined according to triangular probability distribution function. So we will be using this one. And after recruitment and assignment, we'll make a site update. And if it converges, we can eventually stop the code. Coming to the discussion part, we are still working on the project, and we aim to show that there's an increase in performance after implementing the algorithm, as the 2-parameter version has shown its efficient performance in other optimization problems, and we'll be publishing the results soon.
Okay. First of all, thank you for having me in this workshop. Actually, my presentation is about improving the Bees algorithm using a gradual search space reduction. Actually, it's aiming to improve the Bees algorithm. This is the contents of my presentation. It's just a quick overview of the Bees algorithm, then a flow chart and the basic steps, experiment setups and performance metrics, proposed method, and the 5 scenarios of this proposed method, and testing on engineering problems, gear train, and springs, and then my contribution. Okay, so just a quick overview about the Bees algorithm. It was, I think most of you know this, but there might be somebody who doesn't know about this. It is found by Prof. Pham and colleague, okay, in 2005, inspired by the behavior of the bees food foraging. It's the kind of nature-inspired algorithm and include others like PSO, SO, and ABC. It's kind of swarm intelligence, which belong to broader category of meta-heuristic optimization. And meta-heuristic optimization is kind of non-deterministic optimization method, trying to find a near optimal solution for problems where deterministic optimization is infeasible due to large search space. It's trying to find sufficiently good solution, not necessarily the optimal one. Okay, here's just a quick the flow chart about the Bees algorithm, how it's start by taking initial sample and then evaluate the fitness, and then evaluate the fitness of this sample, then searching around these the best ones in a certain neighborhood area, within neighborhood area, then recruit bees for the best bees. There will be more bees for the best bees, and then select the fittest ones, and then also performing some global search, and then at the end we join the search from the local search and the global search to find new population, and it will continue until we find a good solution. Okay, this is also the basic steps. Okay, now the experiment setup for my, let me first try to explain the proposed method. It's actually based on the gradual reduction and elimination of search space as long as no promising result found until a good result found. Okay, this gradual reduction will take place according to 5 different scenarios, and considering the different minimum location in different problems, because for every problem is the optimum can be located, okay, not necessarily in the center, or it can be in anywhere in the search space. The process will continue until the optimum found within a margin of 0.001 or reaching the stopping criterion of 500,000 in FE. That's the number function evaluation. Okay, the search space reduction 5 scenarios is actually the first one is to search the whole search space, decreasing gradually from both ends of the search space by elimination factors of S equals to L divided by N, and L is the length of the search space, N is the number of samples. The next one is to search after the first quarter from the two ends, also with the same elimination factors. Also, the third one is to search the area between the center and the left end of the search space, and decreasing from both ends. And searching area between the center and the right end of the search space, and then decreasing from both ends also with the same elimination factor. Searching the whole search space, which gradually decrease from the left and from the left end by the elimination factor S, as we talked about. Okay, just to go back to explain to you the experiment setup. Actually, the proposed algorithm were tested on 24 benchmark function. This benchmark function was selected to accommodate for different characteristics or topography of these benchmark functions, to make sure that we are covering a wide range of types of these benchmark functions. The benchmark functions themselves are complex mathematical problems. And it is in the literature of the optimization for testing optimization algorithm. It's a common method to challenge the performance of the optimization tools. The performance of the proposed algorithm were compared with the kind of the version of ABC, which is called Quick Artificial Bee Colony QABC, and the standard particle swarm optimization 2011 SBSO 2011 algorithm, because they are the latest of these two types of optimization algorithm. The statistical significance were tested using the Mann-Whitney test. The key performance metrics used to test the performance of the proposed algorithm as first is the accuracy, which is the difference in the fitness value between the standard standard minimum of the stipulated minimum of the benchmark function with the one found by the proposed algorithm. The second performance metrics is the NFV, the number of function evaluation, or we can call it also the speed, which is how many times the objective functions or the benchmark function were executed. And that's actually for 500,000 maximum number of function evaluation. The SR is actually the success rate, which means that the ability for the algorithm to converge in the benchmark function. So if the proposed or if the algorithm will converge in all the algorithms, okay. Sorry, if it will converge on all the benchmark functions, that is 100%. If it's less than that, it will be according to the percentage of the convergence. 50 runs were conducted for every benchmark function until the optimum within a margin of 0.01 found, or the stable criterion of 500,000 NFV reached. Okay. Now we go to the testing result. Okay, it's a summary of the testing result. In terms of accuracy, we can see that in terms of performance, the proposed algorithm won 20 of the 24 benchmark functions, while the QABC 4. For the SBSO 2011, the proposed algorithm won 22 benchmark functions, while SBO is one only and none is one, and the BSO actually the BA for the comparison with the BA, the proposed algorithm won all the 24 benchmark functions. BA wasn't able to when in any, what I mean by BA is the basic algorithm, the basic Bees algorithm. The mean and standard deviation also reflect the stability of the performance, how stable the performance of the proposed algorithm. The statistical significance, so how significant is how statistically significant the result obtained by the proposed algorithm in all the 24 benchmark functions. The success rate actually showing that the proposed algorithm performed very well. It was able to converge in 92% of the benchmark functions, while QABC, for example, 65%, SPSO 2011, 77%, BA 69% only. In terms of evaluation type, also the proposed algorithm achieved also a good result. This is what we mean, what we call speed. So the proposed algorithm was able to was better in or executed less in or needed less number function evaluation against QABC. It's so it won 19 of the function, while QABC in 5 only. And this is also applied to the other algorithms in the comparison. So just to summarize the result, okay, the accuracy figures indicate positive improvement in performance. Also, the statistically significance is it was statistically significant in more than 2/3 of the function in terms of accuracy. Also, the success rate, as we just mentioned, was also better in more than 90%. Also, in terms of speed. Okay, then it was the proposed algorithm was also tested on the gear train problem. It's actually a single objective, single engineering problem without constraints. The gear design actually is for this problem is aiming to minimize the gear ratio to be as close as to 1 by 6.931. So the closer is the better is the result. This is just to give you a quick overview about the gear train problem. We actually the most important thing is here is that to understand this is that we have here we have 4 gears. Here we have D, P, A, and F, and the objective function is about minimizing the ratio, the gear ratio, so to be or the difference in the gear ratio between the okay, the gear ratio and the one found calculated by the algorithm. So actually, this how it's calculated. It is okay, x3 times x2, which is actually this is for the gear number 3 and gear number 2, divided by the x1 and x4. This is okay. This is all the number of teeth for these gears. Okay, so x3 here means the number of teeth of gear 3. X2 is the number of teeth of gear 2, and divided by the number of gears, number of teeth for gear 1 and gear 4. Okay, and then the difference is to squared to find the difference. Okay, actually these parameters, the number of teeth actually take integer value, which is subject to 12 to 16. I mean, the number of teeth need to be between this value, that's 12 and 16. This is actually stipulated by the inventor of this problem. This is the result of testing on gear train problem. It was tested or compared with against the PPA and ABC, BSO, and GA and CS. These algorithms were selected based on their performance on this problem because they have performed very well on this problem. So The result give us just show the performance of the proposed algorithm, which show that it was able to get a good best solution. Okay, and even in terms of speed. Just to comment on the testing result, actually, okay, that the proposed algorithm was competitive to the best performing algorithms, but actually it wasn't very stable in this problem. It's because it's not in the all runs. I mean, didn't give the good result in all the runs. So if we take the mean of the all the runs, the 20 runs that were performed, it doesn't reflect a good, actually a stable performance, which means that there's a need for improvement. In terms of speed, it wasn't very fast, but it can be considered in the middle. Now we move on to testing on the tension comparison, tension compression spring problem. Okay, this is actually as a single objective function with constraints. The aim here is to reduce the spring steel wire volume to decrease the weight of the spring. This is just to give us a quick idea about about this engineering problem, and here it's showing the constraint of this engineering problem. Okay, this is now this is the table here shows the testing result of this of the proposed algorithm against some of the other well-performing algorithm in this problem. Just to comment on the result, actually, we can say that according to the table, that BA, the proposed algorithm, okay, did not perform the original BA in both accuracy and speed, but anyway, it was competitive. It was able to get a good result. The statistical figures, the mean and standard deviation, suggest that it wasn't very stable, it wasn't consistent in performance. In terms of speed, it performed well, but it wasn't the best of the performance. But anyway, it was indicated a good performance. Just to give you a quick idea about the contribution of this research, here we were able to improve the accuracy of the BA with the ability to find the exact global minimum in some benchmark problems. It was able to find the exact minimum. It's not just close to it, but the exact one. The technique used actually have the potential for more improvement. Okay, and the scenario used can be there is a wide variety of scenario that can be applied in this kind of technique. Okay, that also showing the wide possibility of search space manipulation to improve BAs. The search space itself can be manipulated in many different ways. It's actually showing that there's some smarter method to improve the BA, while also at the same time they are very simple, not very complicated. Okay, so that's was my research. Now, if you have any question, you can